All right, so these are your notes on speed and motion, speed and velocity for the first portion of force and motion. And we just need to recognize first what motion is. And motion is just whenever there's a change in position over some period of time. So if the position of an object changes, that means that object has motion. And the way we know that this happens is by using a reference point. A reference point is just some other object that is used to judge motion. Generally, we want to pick something that is not going to be moving. Sometimes we have things that are good reference points, other times we have things that are bad reference points, but reference points are just used to compare the motion of objects. So if you can imagine this scenario where you've been on a bus, maybe before the buses pull out of the loading area, or if you've ever been in your parents' car and you're stuck in traffic and you're in the passenger seat. In the other case, you're just like not really paying attention to what's going on around you. Maybe you're playing on your phone, or you're reading a book, or whatever the case may be. And then all of a sudden you get that feeling like you're rolling backwards a little bit, and you quickly look up and look around, and you notice that you're not rolling backwards, but instead the car or the bus next to you has started to pull forward. Subconsciously you used that other vehicle as a reference point, and when you started to notice that your position relative to that other object was moving, or that position was changing rather, you assumed for just a split second that you were in motion until you looked up, looked around, and took in some additional reference points to recognize you're not moving, but instead the vehicle next to you is moving. So that's a reference point, but it's a bad one. Ideally, we want to pick reference points that aren't going to move. Things like trees and buildings and street signs. These are things that are not going to move in the grand scheme of things. Now, we recognize we can always say, well, everything on Earth is moving because Earth is moving. And how do we know that Earth is moving? We judge it by the sun, and we move around the sun. But then the sun is moving, moving around the center of the galaxy, and the universe is expanding. So we can recognize that we can always say that everything that we know of on Earth here is moving. But really, this year we're going to be talking kind of more like kind of line of sight, smaller scale sort of movement within Earth, or at least very close to Earth. So we want to pick good reference points when we're judging the motion of objects, things that are not likely to be moving, and that's kind of ideal for judging motion. Now we can judge ways that things move in different ways. We can judge how far something goes. We can judge how much time things have been moving for. And with those two pieces of information, we can identify the speed that an object is moving. And speed is just the rate at which the object moves. I know in some math classes you've been talking about rate already. In this case, speed is that rate. It's a measure of motion over time, and that's all rate is. It's something over time. Now, when we talk about speed, we talk about average speed, and that's because things constantly speed up, slow down, they stop, they go. If you're going, when I come into work every morning, I don't jump into a car that's traveling at 55 miles per hour. I instead get into a car that's already at a stop, and then I start to go, and I'm going to run into some stop signs, so I'm going to have to slow down and ultimately come to a stop, and then I'm going to have to start going from there, and I'm going to merge onto the highway, so I'm going to speed up a little bit, and then there's a traffic jam, so I've got to slow back down again. So these things are constantly, your speed is constantly changing, and there is such a thing as instantaneous speed, which is the speed at any given instant in time, but that's not really what we're going to be looking at this year. We're going to be looking at average speed, and we can calculate average speed. We can do this by taking the average speed being equal to the total distance traveled divided by the total time it takes for the object to travel that distance. So this, we know some of these SI units. The SI unit for distance is going to be meters, and the SI unit for time is seconds. So those are the two units. We use SI units for those, and if we take those together, that gives us our average speed SI unit, which is meters per second. And this essentially tells you how many meters are traveled in just 1 second worth of time. Now, we don't always measure average speed in meters per second. In the same, we don't always measure distance in meters, or always measure time in seconds. So your speed unit, while the SI unit is meters per second, the unit that we're going to use on a question-to-question basis or a scenario-to-scenario basis is going to be based upon what our distance unit is and what our time unit is. So if we've measured distance in kilometers and time in hours, then our speed unit is going to be kilometers per hour. On the other hand, we also need to be able to solve for the other variables in this equation. So sometimes I'm trying to solve for time, and whatever the time portion of my speed unit is, that's the time portion I'd be providing as an answer if I'm solving for time. Or whatever the distance portion is from my speed unit, that's going to be the unit for my distance when I'm solving for distance, unless you're told otherwise. Sometimes you might get speed in meters per second, but need to solve for distance in kilometers. So you need to be able to do those kilometers to meters conversions and vice versa. They're important. Now, when you look at this, you can see it's essentially just an algebraic equation. Our average speed is equal to total distance over time, but average speed is really average speed over 1. This is not a math class, so I'm not going to judge your ability to do algebra. Instead, I'm going to give an alternative method, and this is the method we'll use in class a lot. I would call it the triangle method. So for this, I just take a triangle, and within that triangle, I put a T to create the top portion and 2 bottom portions. And then when I look at this formula, I have average speed equals, and then total distance is what's highest up in my formula. So if I have speed equals distance divided by time, distance is what's highest up in the formula, so that's what's going to go in the top of my triangle. I put distance, and then, sorry, that's a little on the rough side here, trying to draw with the mouse. So that's distance is what's going to go in the top triangle, and the top of the triangle, and then the other 2 variables, speed and time, would go in the bottom triangle. And it's really easy to figure out kind of what you need to do in order to solve for the various variables here. So if you're solving for speed, you just cover speed up, and when you cover up speed, you have that speed is equal to distance over time. And that means that in order to solve for speed, I take distance divided by time. On the other hand, if I'm trying to solve for time, I'd cover up my t, and that would leave time is equal to distance over speed. Now, if I'm trying to solve for distance, I would cover that up, and I have 2 variables next to one another. If they're next to one another, you multiply. So distance, if I cover this up, and that's equal to speed multiplied by time, and that will tell me how far I've gone, keeping all my units consistent. So that's one way that we can solve these formulas. And a lot of the formulas you're going to look at this year are going to be this format where something is equal to a fraction. The other format we'll look at a lot this year is going to be something equals 2 things that are multiplied together. And when we have it in this format, the item that is isolated, in this case distance, that's what goes to the top of the triangle. So we're going to see a lot of equations that are going to be in this format, something equals a fraction, or in this format, something equals 2 things multiplied together. In either case, we can put them into this triangle, where what's up top goes up top, or what's isolated goes up top, if they're all in one line. So, and then within the triangle, we can use that by covering up the variable that we're trying to solve for, and what's left over, that tells us whether we're going to multiply if they're next to one another, or divide if they're on top and below each other. So that's kind of the method we're going to be talking a lot this year. It's called the triangle method. And so looking a little prettier, this is how it fits in, is that we distance divided by speed to solve for time, or distance divided by time to solve for speed, or speed multiplied by time to solve for distance. So if you take a second and try to figure out what these next equations are, I'm going to put 2 equations up. I want you to take just a couple minutes, pause the video, try and solve the 2 of the equations. Here are your 2 equations. First one, you take a 7.5 kilometer hike north on the mountain, and it took you 1.5 hours. What was your speed? And then second question is, your family took a trip. You drove for 5 hours and went 443 kilometers. What was your average speed? So in both occasions, you're trying to solve for average speed. So just pause the video, take a minute, and try to solve these equations. Alright, so hopefully you solved these equations, and you started off with speed equals distance divided by time, and so you then just replace the variables that you knew. Your distance was 7.5 kilometers, and then that was over your time of 1.5 hours. And then we have these handy dandy little devices that you can punch numbers into and it does calculations for us automatically. I do not expect you to do all your math by hand. Please feel free to use calculators. So when you do 7.5 divided by 1.5, you get 5. And then you need to remember to make sure you put your unit here. So it's kilometers per hour is my unit. So I do kilometers per, it's the slash, and then hour is going to be our unit here. So that's how we would calculate the first one. Now, when we do equations this year, we're always going to be taking 3 points. A point for your setup, which is essentially this, and a point for your numerical unit, and a point for your unit for the problem or for the question. So you need to have all 3 of those things provided whenever you do a calculation on a test or quiz or lab. You need to have the setup, the numerical portion of your answer, and the unit for your answer. When you look at the second question here, you have 443 kilometers divided by 5 hours, and when you do that, you get 88.6 kilometers per hour as your answer. And so with this, we can kind of notice that not all units or not all answers are going to be a whole number. We should not be rounding the whole numbers unless you're told to do so. As a good rule of thumb, we're going to go 2 decimal places. So you should be rounding to the hundredths place unless either you're otherwise told. If a problem tells you to round to the nearest whole number, then do that. If the problem tells you to round to the thousandths place, then do that. But we should round to the hundredths place most of the time. The other exception to that is going to be if we have a number that's like 0.0000746. If we rounded to the hundredths place, we would end up with 0.0 and then whatever our unit would be. That's not necessarily telling us the whole story. So if you have a whole, a really tiny number way past the hundredths place, then you should round your number to include 2 numbers that are not 0. So in this case, we would round to 0.0007, and then this 4 becomes a 5 because of the 6. When we round that, we're going to round the 5 up. So it'd be 0.000075 plus whatever our unit would be. So you should kind of keep that in mind when you're doing your homework, doing calculations for tests, quizzes, is generally we're going to round to the hundredths place unless we're told otherwise, which is kind of scenario 1 or scenario 2, that rounding to 2 decimal places just wouldn't make sense. So that's speed. Speed is just a ratio of distance over time, but it's not the only way we can measure motion. Another way we can measure is with velocity, and velocity is just speed plus a direction. So if speed is 100 kilometers per hour, then velocity would be like 100 kilometers per hour west. The speed portion of it, the 100 kilometers per hour, is calculated the exact same way, but then you also have to provide a direction for it. So when you're calculating velocity, it's just important to make sure you put that direction. So if we look back at this question here that we had just answered the speed for, we said the speed was 5 kilometers per hour. So then the direction would be 5 kilometers per hour north. That would be the velocity when we look at the whole thing, 5 kilometers per hour north, because the north is provided to us in the question. Sometimes we get questions like the second question where direction is not provided. So we did 443 kilometers divided by 5 hours to get 88.6 kilometers per hour, but there's no direction provided. So a kind of general safe direction, if there's not one provided in the question and you're actually asked for velocity, or you need to come up with a direction based on the variable you're solving for, would be to say forward. So we would say like 88.6 kilometers per hour forward, and that's a way for us to list the direction. Sometimes you'll have questions where the direction isn't actually told to you, but you should be able to figure it out. Like if you're traveling from New York to Florida, you should know that that's south. So you should be able to put south as a direction. Or if you're traveling from California to Virginia, you should know that that's traveling east. So you should be able to put east as a direction. Now, the big difference between speed and velocity is really simply that velocity includes this direction. So the two factors that really control what your velocity are speed and direction. That means if your speed changes, your velocity changed. But also if your direction changed, your velocity changed. So when baseball pitchers throw a ball, even if that ball is traveling the exact same speed all the way to the mound, it's changing direction, and therefore it's changing velocity. It always kills me when baseball announcers talk about a pitcher's velocity changing. Their velocity is changing with every pitch because the direction is constantly changing. Just like if you were, I live near a motorcycle track at Summit Point, and so on Saturday mornings I can hear the motorcycles. They're riding around a circular track just over and over and over and over and over again. Even if they lock in at one particular speed, say it's like 150 kilometers per hour, or let's say 150 miles per hour, they would be constantly changing direction, and therefore their velocity would be constantly changing. So their speed could stay the same while their velocity changes if the direction itself is changing. So there's another type of, or a specific type of velocity we need to talk about, which is resultant velocity. And resultant velocity includes that word result. And so when we think about resultant velocity, we're talking about taking multiple different velocities that are affecting an object and combining them together. So if you can imagine a scenario where you're on a bus and the bus is traveling east and it's traveling at 15 meters per second. So if the bus is traveling at 15 meters per second east, that's the bus's velocity. But on that bus, you stand up and you walk toward the front of the bus. If you're walking at 2 meters per second, well, your total velocity includes the 2 meters per second that you're walking, but it also includes the 15 meters per second that the bus is traveling. So you need to combine those. Now, if you're walking toward the front of the bus and the bus is traveling east, that means you're also walking east. So you're just going to combine these. So you're going to add these two velocities together. 15 meters per second plus 2 meters per second would give you a total of 17 meters per second with east as your direction. So 17 meters per second east would be your resultant velocity. On the other hand, if you were to walk toward the back of the bus, now you have to subtract these velocities. So the bus is traveling at 15 meters per second east. You would be walking at 2 meters per second, but in this case you'd be walking west. So if you were to be walking west instead of east, and kind of cross out this east thing, you would not have 17 meters per second east, but rather have 13 meters per second, because you're going to subtract your two measures since they're in opposite directions, and 15 minus 2 would give you 13 meters per second. And then you take the direction of the greater value east. Even if you're walking toward the back of the bus, you're still overall traveling eastward. So when you have to do resultant velocity for velocities that are in opposite directions, you need to subtract and then take the direction of the greater value. Lastly, we want to talk about terminal velocity. And terminal velocity is the greatest velocity that an object can achieve. Normally we talk about it when objects are falling. So if a human was to jump out of an airplane, they're going skydiving, their maximal velocity is going to be about 56 meters per second. But they can ultimately pull out a parachute and let that go. And then when they do this, they change their shape and size of themselves plus the parachute. And that changes their terminal velocity. So the maximum speed would be only about 5.5 meters per second. This is because you have a change in shape and size. So it's actually air resistance that causes terminal velocity. And that change in terminal velocity can be achieved by changing the shape or size of the object that's falling. All right, that's it. Make sure you check out the second part to these notes. Have a good one.